Good morning, geek fans. Today, topic 2 from Fundamentals of Design, creating ideas. Today's motif is pirates. Arg! You got to be a little different. You got to be ready to board new ideas. And notice the motif. We got some black, and it's not really white, but that means that's the whole thing. Nothing is really black and white when you're creating ideas, right? It's the full spectrum. So that's what we want to go into. We got a bunch of different modules we're going to cover within this topic today. So let's launch right in. Our topics, we're going to go from creating ideas, course defined, some thought processing. We're going to do some experimentation with our infamous drill press. How do you do drawings and sketch your ideas to get your initial thoughts? Research. What are you going to do for research? We'll do some fun research real time there. And then how do you write about it? Because in the process of writing down your ideas, one, you document them for patents and blah, blah, blah. But writing is a fantastic, powerful, creative tool to which to pull ideas deep from within the cortex of the mind. Yep. And then we go into full power geek mode. How do you actually first order analysis of your ideas to make sure they're sane? Because physics doesn't give a darn. And then how do you evolve these ideas to get launched into the next phase, which we'll cover later? Let's dive right in. This slide is a little fine for you to see here at the board, but it shows this flow of ideas, course to fine. Remember last time we talked about the drill press and what the different modules are and the different sub-teams we're going to work on according to their passion. My passion happened to be the table, how I want to redo the table. And I'm going to start from a very broad mode, thinking about what's wrong with the current design, or nothing's really wrong with the current design. The product was released, it was a great product, but there's always opportunities for improvement, and how we're going to think about different ways of doing things, do the analysis, start doing models, finer and finer, until in the end, we're going to end up with part drawings. And that flow of ideas, where you go from strategies, different concepts, pick a concept, different modules. The modules, each module then will have different components, and then finally the individual elements which you do the part drawings for, or the bill of materials to order things. Now, let's dive into the thought process. Remember we talked about passion last time. There's this neat quote here by Jacques-Lucien Monod. Personal self-satisfaction is the death of the scientist. Collective self-satisfaction is the death of research. See, pirate stuff. It is restlessness, anxiety, dissatisfaction, agony of the mind that nourishes science. You want more. Nicely, though. So it's this driving hunger, always ask why, that we're going to explore. Never be complacent, because the minute you sit back and you say, yeah, that was really good, yeah. Then someone else says, he did a really good job, but I'm hungry. I'm going to take it with him from while he's just sitting there being happy, okay? So when you're looking to generate ideas, you want to assume right out of the box that whatever you've done, your competition is going to try to take it away from you, to do better. And that's the essence of capitalism and the ever-increasing growth of humanity. So you want to be involved with thinking about how you're going to defeat your idea even before you have the idea. This will then generate a lot of different pathways for you to explore. Even when you find one pathway that you do go down to explore, you will have started making this map of these other pathways along the way that you can later on also explore once you've launched the product. That will help you be coming out with next generation products. So let's go through some of these high-level, really, really good cues. And remember, this stuff has been around since humans first started making stuff, okay? It's really important that we recognize that there's a lot of history behind how these methods have evolved. So the first thing is systematic variation. What are all the possibilities that you may be able to think of? For example, on this table, here's a table, and it's held with an arm, and the arm goes up and down. Well, how many different variances are there? And as you'll learn in topic 3, and we mentioned a little bit before, the concept of reciprocity, here, the table goes up and down. Well, if I have workpiece on here, maybe this whole head should come up and down and the table should basically stay fixed most of the time. You may say, well, but you can have different size work pieces. So, okay, so these are the type of point counterpoints you constantly want to wrestle in your mind. You want a persistent questioning. Always ask who? Who's going to be using this? What? What are they going to be drilling on this thing? What kind of parts? And not make something that will handle 100% of everything. But if you were to go and to be designing a consumer product like this drill press, interview hundreds of people and look at the stuff that they typically make, that they want to drill, and you design for the 80 or 90% of the people, or their parts that they're going to make, and you focus on that to solve the biggest picture. Why? Why would they want to buy your thing as opposed to what's out there already? Why are you doing this? Why is yours better? Where? Where are you going to sell it? Where is it going to be located in the room? Every question you want to think about, you can always preference with where. And now watch this trick. If you take one of these things like where, and now you play the game, and this is a little prelude to later on we're doing writing. This is the power of words for creating ideas, even deep techno-geeky things. Where? Now you fill in all the possibilities, and you do this, by the way, with each one of these questions. Where is it used? Right? Where might it fail? You see what we're doing? We're taking all the different kind of qualifiers. Where is it used? Where might it fail? Where, what else? Well, you fill in what's here, where. Okay? And now you can play the game with, you can almost make this into a game. And what I did when my kids were being raised, or they were raising me, I would work at home. And I would play this game with them. And they thought it was the best thing. They had no clue that Daddy was designing a new grinding machine. We were just playing this game with words. We were building with Legos. So this is the way you can kind of jumble that, have your career and eat it too. Okay? And how? How's it going to be used? How will you be sued if it breaks? So always be thinking of safety also. Now, after your persistent questioning, you now look at these concepts of reversal, forward steps and backward steps. Start with an idea, and then as many ways as possible, create different ideas until each gets to the end goal. This is also called this idea of diverging thought. The opposite of that, by the way, is start with the end goal and work backwards along as many paths as possible till you get to the beginning. Let's do an example with the drill press here. Now, whenever you're designing a machine, in general you have what's called the tool. Here I'll just draw a drill bit. And then you have the workpiece. And here's the hole that's going to go into the workpiece. Now, the very simple thing is we're assuming that you have a drill and it's going to drill a hole in the workpiece. There's the broader question of maybe you don't want to use a drill, maybe you want to use a water jet cutter or a laser. But for now, we'll assume this is a given home workshop drill workpiece. It's very simple. Now you just got to fill in the rest of the machine. Okay, so think about that in terms of forward steps. What's your idea and how many ways can you move forward until you get to the end goal? And that would be the workpiece is here, for example, and I want to position it to here and then connect it to the drill. Okay, so I've got some kind of a table, and now I want to go X direction, Y direction, and do I want to also rotate it? So if the part is fixtured on there, I can move it and rotate it. And notice what I'm doing in my hands. My body is becoming the part. Make your mind think about the problem, and your body actually now be the part, the tool, and the part. Start to live and become the machine about which you are thinking. It's very important to put yourself in that groove. Okay? So I'm going to, in one place, I need to take a part with a hole in it. Part with hole. I'm here and I'm drilling. Now I want to move the part. Right? How would I start with an idea for moving it in as many ways possible to connect it to that end goal? What does that mean? That means that I'm going to go back and say, where's my pen? Here is a structure to which the drill is attached. My part is here and I want to move it. So now starting from the structure, how do I project forward and all the possible ways to get to the end point to move this thing. I can have an arm and another arm. And now watch what I'm doing. I'm jumping ahead a little bit. I'm building arms based on revolute joints or round joints. Later on we'll show you that in the linkages topic 4, the other types of joints are XY or Cartesian joints. So I started here and I want to get there and have that thing move, so I'm going to reach out and then with my arms be able to move it around. Okay, that's this task here. We're moving forward. And that's going to have revolute joints or Cartesian joints. Backward step. Let me start with the part and go back to the structure. So for example, I'm here, I'm the part, and I want to move around, and I got to get back there to the column. What am I going to do? Well, I want to move back, and I want to move over. So this kind of is almost naturally starting to make me think of some sort of a slide system. And I want to move back, and then I want to move over. So back here on the column, I have a T-based with another slide. And let me use a different color so you can see what we're talking about. That I now have this first slide moves in and out, and then back and forth I will draw a sketch for an axis that moves that way. Right? So my green axis moves in and out. The green axis is moving my part in and out, and the pink axis is moving back and forth. Now, I still got to rotate my part, so I say, well, okay, I'm going to put here, I'm rotating, so I'm going to put an axis at the end. Now you see what we did was, very much in real time, when I started thinking about when I'm back here and I want to go out there and have that thing move, you see, when I'm looking at something up there moving, and it could be in a bunch of other ways, I start thinking about rotations, for example. When I'm here and I start thinking about moving back and forth, I'm more in a linear mode of thinking. So this kind of idea of placing yourself at two different perspectives and accomplishing the motions you want, different people may have thought completely the opposite. But the point is you're putting yourself in a different frame of reference, little joke, in order to see different ways of moving things. This is really, really critical to help you explore different types of mechanism. Nature's way. How would nature solve this problem? What would nature do to move this to this? Maybe it's going to fix this and then move this guy up and down, like, this is a fixed part, then asteroid comes through. And then exact constraints. What are the minimum amounts of motions that I need to do? And as we'll see in topic 4, something called Grashoff's equation will help us determine that when we have links moving around in space, what is the minimum number of joints we need in order to accomplish the motion? Systematic variation. Now I'm going to build on this preliminary thinking. Think of all the different ways you can make joints to do this. Think of all the different joints you can move in and out. How would you apply the energy to move things? Is this going to be moved by a person? Or are you going to design the system to ultimately be able to put little motors on it so you press the button and the part moves automatically? You're starting to build a machine tool. Maybe I can sell a drill press that I've designed that's very low cost and very ergonomic and easy to move around. And then that's only $99 for the basic drill press. And then for only another $99 a month, for 99 months, you can now have it controlled by your iPhone. So you can take your smartphone and and the drill press will move. How's that for a product idea? Okay. So that's one of the things what systematic variation will help you start to do with your idea is when you start thinking about all the different ways that energy can be applied, stored to the system, whether it's manual or by a machine, you'll start to think of new ideas. Wow, maybe it's not just a manual machine. Maybe it's actually a computer-controlled machine. Materials. What kind of materials are you going to make this from? Let's vary all the different things you can think about. Traditionally, you think of machines and they're made of steel. Well, what if it was plastic? Cheap plastic, stupid thing. Or, wow, that's really incredible the way you use carbon reinforced super ultra double extra special plastic. So don't be shy about trying different types of materials. What are you familiar with? You know, I always use this. So then say to yourself, remember systematic variation, what am I scared of? What have I never ever used before? Let me try that. Now's the time to do it, the very early stage of idea creation. And when you start thinking about using different materials, different concepts for the design will actually pop into your head. Motions, as we just mentioned through, linear rotary motions, controls, passive, like I'm moving it by myself, or active, it's going to be computer controlled. All the combinations of the above. And as you're doing this, because you have this training, you're going to school, and you want to meld with the textbooks and teachings of your life. How am I going to write the equations to describe the design so ultimately in that design I can optimize it? Here's an example. If I have my machine and it's moving and it requires a certain amount of time to move, let's say I want to take this part and move it some distance x in some time t. How is the power related to that? Power will go by, if the distance gets longer, it's going to take more power. If it goes faster, it's going to take more power. So if time goes down, is it just this? Well, we'll see. There's a magic surprise here that happens. If you just assume that and start designing your machine that way, you're very, very wrong. Turns out there's this exponent here. What is it? Reversal. You've heard me use this term a bunch, and now I want to describe how I got through a lot of my schooling days. You're often faced with a challenge. You need to prove this. And you think, ooh, I'm starting here. Oh, I've got to prove that over there. This is a really fun problem. Here's this figure. It's a tetrahedron. And it's a very, very simple. Given the length equalities given by the colored pointy end cylinders, prove that the yellow cylinder is the perpendicular bisector of the purple and red cylinders. In other words, you have to prove that this yellow line here is perpendicular to the reds and the purples. That is a very, very difficult problem to prove. It's one of those honors geometry problems. Whoa. So if you just look only at that and you start working through it, oh, how am I going to do that? Let's see. And you go, and you hope an idea goes, and pops into your brain. No. That's too much work. You could have an aneurysm doing that. Don't be shy. Say, well, I have no clue how to do this. So you know what? I know in engineering, stability by triangles. So one of the most powerful tools in the reversal process is says, they asked me to prove this, right? Right. Therefore, I'm going to assume it's correct, that I know this is a right angle. And now, because I'm doing a geometry problem or an engineering problem, I know that. See, you pushed too hard and the idea just went poof. Triangles. Always take your pen and draw triangles on stuff. Where can I put triangles on there? Well, I've got a vertex here, and I can put a triangle. Whee! And I've got another vertex here, right? Whee! And I can go whee! And make all kinds of triangles. See? Whee! Any more triangles to be formed? No. Now you start the process off, okay, assuming this is a right angle. So when you say prove or do, and in the end you say, that's ancient Latin for modern Latin of QED, which means we be done. So in the end I'm going to say, df squared plus fe squared equals de squared if it's a right triangle, for example. So you just start writing and you go back up that way. Okay? In other words, I know that these two are equal, and if this is a right angle and that's a right angle, that these two triangles will be similar. Okay? So read the text and you'll see the details, or you try it yourself before you read the details and work from the bottom to the top. If you see how to go from the top to the bottom, that's fine. But whenever you're stuck, reverse it. Likewise, whenever you've got something that you think is fantastic, you've come up with a really, really brilliant idea. I've got this drill press here, and I've got this part I'm going to be drilling. God, it's such a good design. Drill moves down into part. What's the opposite of that? Why can't I have the drill below and the part move down onto the drill? Why would you ever want to do that? Well, anybody who's drilled knows that when you start drilling, you get all kinds of chips in here. And if I do it upside down, the chips will fall. So yeah, but the part will fall. So this idea, and you'll also see, is called persistent questioning. Well, why don't I fixture the part here, and when I'm ready to drill, I flip it over? Using reversal again. Very, very powerful, powerful, powerful technique. 1 over ouch equals ah. Okay? One of the most powerful methods I use to defeat the enemy designers. Well, to compete nicely. So I'll take whatever they've done and I'll do the complete opposite. Complete opposite. I'll explore the complete opposite and see what design I get. Sometimes it's better. Okay? That's it for this module. Start thinking.